Hello. Hello, Chair.
Hi, sir.
Hello.
Yeah. Hi, Siddharth.
Yeah.
So we will start the discussion. So I think Surya and you are the uh, working on this problem on QSVT. So what we thought that since it's a bit complex task, so we will merge Surya and you, and so that it's easier for you to divide the task and code and develop the theories.
Yeah.
So I think Surya, you have not met Siddharth. So please, I mean, introduce yourself to each other. So I think Surya, you may go first.
Yeah, so myself, Siddharth, I just joined the team as an intern, and I have experience working with Q Street and Pennylights, and as a part of my final project, I do have designed quantum support vector machine. So I guess I would be able to go ahead with this task with the help of them.
I'm Siddharth. I'm a student at IIT Hyderabad, and I have experience with quantum algorithms. I did a couple of courses in that. Qiskit, I have a bit of experience. I've done a lot of machine learning. Yeah.
Okay,
Yeah, hi Britan. Sorry for the delay. Yeah,
no issues. So let's start. Um,
yeah.
would
Let's
you
start.
would you
So,
present or would you like to like take the lead
yeah,
from Surya or Siddharth to present it, and you might explain that.
anything is fine. I'll present for now. I can present the
Okay,
code. I can
sure.
present slides.
Okay. So I just got a bad throat, so I will avoid speaking. Okay.
Sure, sure.
Okay.
Yeah, due to pollution, air pollution.
No, it's due to the change of weather here.
Okay. Yeah. Okay. Is my screen visible?
Yeah.
Okay. So, okay. Just give me a sec. This is your QS.
Guys, I hope you guys have like pen or paper with you so that you may want to write some specific points. Although this meet is being transcribed, but for your convenience, you may keep pen and paper with you so that you.
Okay. Still ingestion is coming. See. Just a second. I'm facing some issue here. It's on desktop. It's not on desktop. Okay, yeah, it's there on desktop, fortunately. Yeah, so this is our main go-to model for now. So hi Siddhant, hi Surya. So this is our main model for now, as in by only itself by classification approach. So how we'll do that. I will touch upon it briefly. But for now, so these are your tasks and what models we have. So before going to this detail, so I don't have any document prepared for this now, but I'll just give you a I can draw on OneNote, but I don't have a writing pad with me, so bear with me the bad handwriting. I'll give you a brief overview of what exactly our model is, and then from then we'll take over. Okay. Okay. So I'll just explain what the model is. We have our input vector. Okay. There is some lag. So we have our input vectors. Okay, like you already know, like yesterday we have taken MNIST data set. MNIST data set is in RGB format. It's not in RGB format, sorry, it's in grayscale format directly. As in the data set is available on Kaggle only in grayscale format, and it's available from 1990s in grayscale format only. So no need to convert into like a RGB and then grayscale. So once that is done, we'll flatten it, and then for simplicity, let's consider first as the amplitude encoding. That in the task it is mentioned like you have to consider all the encodings, but let's consider only amplitude encoding. In that amplitude encoding, I'm just considering a single vector of a particular class. It may be any class 0, class 1, class 2, class 3. Okay, this is clear, I hope so. And this vector is of size 1024 cross 1. Generally, I don't know if I reduced it dimensionally there, but we'll look over the code. Okay, so after this, we are applying a kernel matrix. A kernel matrix. So what exactly is a kernel matrix? If you look into SVM, a general convention of SVM is you will multiply or your dot product your
Sweta,
vector.
uh, sorry to interrupt. Sweta, you may join at 9:30. Okay,
Oh, okay.
this is a different project that is being discussed right now.
Okay, sir.
Okay. So Siddhant and Surya, so we have taken a vector, we are dot producting it with a kernel matrix, dot producting or multiplying it with a kernel matrix. So as in, we are not specifically dot producting, we're dot producting the back size of this with this array. But we'll look at the operation, how it is done in the code. But for now, we're taking a matrix, a kernel matrix. It has a dimension, input dimension of 1024 cross. The second dimension is up to you. This dimension is called as, is taken as support vector here. Okay, this might be, if you are familiar with your support vector, conventional support vector machine, this is totally different from that. Like not totally different from that. I'll come over the similarities when we look over the code. But for now, as consider this as a support vector, like number of support vectors are equal to 0 only in the dual Lagrangian equation. But for now, we are taking this as support vectors. We are multiplying that with our given vector, and this is a trainable matrix. Okay, this is a trainable matrix. So why we are doing that? Because if you are aware about LLM models, like what LLM model does, it multiplies with query matrices, key matrices, value matrices, right? Means it finds the optimum linear embedding that a vector can get of a particular class, if you're getting the point. So we have 5,000 vectors in class 0, 5,000 vectors in class 1, and like so on. 50,000 vectors in total. We have curved that data set. Actually, it is 60,000, but we have curved that to like equal balancing. So, we have this 5,000 vectors of class, single class. We have converted that into batch size. So we'll have some 32 or some 64 cross 1024 vectors here, and we are multiplying that with the kernel matrix. Okay. Then you'll have some 64 cross SV size of the array. What you will get here, right? If you're getting the point, then like this is a trainable matrix. Then what you're doing is applying Taylor series on this. Taylor series, as in you have found your optimum embedding, inner embedding you have found, then you're applying Taylor series, as in Taylor series about point A. So Taylor series. Okay, I will just write it here. If you're aware about Taylor series, what exactly is a Taylor series? A general form of the Taylor series is what? F of x plus f of x minus a into f dash of x upon 2 factorial plus so on plus x minus a square upon 2 factorial into f double dash of a and so on. So you're aware about that, right? X equal to a you are putting there. You're aware about this
Sir, sir, excuse
form,
me,
right?
sir. Sorry to interrupt you, but I have a question. I have a
Siddhant
question.
and
Can
Surya,
I
are you
ask?
aware about this form Taylor series?
Yeah. That Surya has a question.
Sure, please go ahead.
Sir, so the kernel matrix which we have just discussed, so this is a classical kernel matrix, right?
Yeah, please go ahead. Like, am I audible? What is that? Which kernel matrix? Could you please repeat? Your voice is not clearly audible. Hello?
Now I'm audible, sir. Hello, am I
Yes,
audible
you're
now?
audible. Like, you're in bit. Yeah. Please go ahead.
Yeah. So the kernel matrix which we have just discussed, so is it a classical one?
So like this method is
Hello?
totally classical. Yeah. Surya. So this method, like, I can get to your point on question. This method is totally classical. It is not quantum inspired. But if you're getting the inspiration from classical, like quantum methods, is where like, are you aware about the like the decomposition? So what exactly is the name of the decomposition? Where you're using Becker-Haidendorff formula. The name of that equation is what, Pritam? I
Suzuki-Trotter decomposition.
Yeah, so what exactly it does is e raised to minus h into if it is a multiple term. Conventional is if it is a matrix, you cannot write in terms of a e raised to a plus e raised to b. If you're getting the point, e raised to
What did
a
you
is
say the name of the D? Could
trot,
Trotterization, basically.
e raised to yeah e raised to a plus b. If they are scalars, na, you can write it in terms of this form: e raised to a into e raised to b, right? This is the form. Like, you can write it in this form. But matrices, you cannot write it directly in terms of this form, so you have to incorporate the like a comma b terms and the higher order terms as well here. So that is where the tree, like Suzuki decomposition, comes into picture. And here you're applying basically the Wicker-Heiser formula, and in that Taylor series is used. So from the inspiration, like, you can take the inspiration for here, but Taylor series is totally, like, this is totally an independent approach of like a quantum spread. It's not a quantum spread approach. Is it clear?
Got it, sir. Yeah, I got it, sir.
Yeah, yeah, sure. So let's go ahead. So this is our Taylor series about point A. Then like we want to classify it. So we have 10 labels, right? We have 10 labels, and this is just one of the labels we're applying or training it on. Okay. So whatever size you will get, it will be of the size support vectors, right? It will be of the size for a single vector. It will be of the size support vectors, right? So if you will add it, basically, if you will add it along that dimension itself, you'll get a single value. So why you're adding along that dimension? Because you want to convert that into single value. So like, if you're taking a sigmoid function, what does the sigmoid function or softmax function does? Basically, it converts into 0 to 1 values. So similarly here, what will addition along that axis will do, or sum around that dimension specifically will do, will convert into single value, and that single value will be nothing but your y. So hope you like got the gist of what exactly our model is. So what we are basically doing, if you look into classically, like if you look into terms of neural networks, what you're basically doing, this is your weight matrix in neural network. Okay, then you're replacing all your activation functions and subsequent weight matrices by Taylor series. You're getting the point? So per class, and that too, but neural network is not limited to per class. Like, you're applying all the vectors in a single, like, a neural network. So what exactly happens in a neural network is, like, a single neuron can be activated, can be deactivated with the help of ReLU functions, if you are aware of that. So that particular phenomena here will not be occurring, because like you don't have specific on and off, like, kind of situation of activation and deactivation of a neuron. So for incorporating that for a particular class, you are applying this kernel matrix and Taylor series separately. But later, like for saving computational time, you can share these kernel matrices as well in between the classes. You can share Taylor series as well, and those forms the subsequent types. We will go into the details of the type, but hope this is clear. And this will be your y, and that so this will be your y. But what this y will be, if you look into like now, hope this is clear in terms of comparison with a neural network.
So what do you mean exactly by applying Taylor series? Like we are approximating the
Now,
forward.
what this when you'll apply it for 10 classes, you take a vector, right? Batch size, you'll get a vector here. A batch size comma vector, right? The size of this kernel will be a batch size comma vector because you're multiplying this kernel matrix with this, right? Which has a size of 1024 cross 1.
Yeah.
Yeah, so what you'll get, this size will be of support vector, right? This will have a size
Yeah.
of support vector.
Yeah.
You will add along this dimension. You will add along this dimension, you'll get a single y value, right? And that y is nothing but your classification label. So now we'll come back to how it relates to your SVM. So conventional XPM, if you're aware about, if it is a single class classification, and let's say you have your data points like this. That's why I'm taking like I have taken this. You can find this example anywhere. Like so your circle will be a segregating boundary here. So it is a second order term, right? So basically, your kernel matrix, what you're using here, can't exactly distinguish this boundary for this. So this is just a two-class example. So if it is a two-class example, you don't require to use a separate Taylor series and separate kernel matrix for every label, because a single label will be enough to classify, because this y value will denote if it is a particular class, it will be okay. If it is not of that class, then it will be another class. So you don't need to do this operation again. But for multi classes, if there are more than one classes, then in that case you will follow the OVR approach, one versus rest approach, or OVO approach, one versus one approach. As in one versus rest approach is what exactly? You will take that particular. So suppose this is class 1 data and this is class 2 data and this is suppose class 3 data. Okay. So what you will do basically in one versus rest approach, you will find a boundary of segregation such that this class 1 is separated from the remaining two classes. This boundary of segregation will be given by your first Taylor series, as in first operation, as in this operation what you did for particular class. Now when you consider the second class, this second class will give a boundary such that it will segregate between these two classes. Now this third time, if you consider, this will give a boundary such that so how many support vectors will come? Basically number of classes and number of support vectors, or the number of boundaries of segregations will be same. So number of boundaries of segregation, nothing but how many times you have to apply this phenomena, as in this operations. So that will essentially give us the boundaries, the number of boundaries. So this is the whole and soul of the algorithm. And now, like for image classification, generally what we do, we use a convolutional layers and max pooling layers at the start, and convolutional neural net is said to perform better for image classification approaches. So that's why, like, the thought process was incorporation of convolutional layers here. So you are all familiar with backpropagation. How does it work, right? So there will be a cross entropy loss here, basically. So whatever value you'll get, you'll initialize this to a random numbers. Then it will be like the y value you'll get here, and by backpropagation, that is the minimization of the loss function, maybe cross entropy, maybe hinge loss. You will update this parameter. So parameters, by what I mean by parameters, as in all the kernel matrices values, as in 1024 cross this, all the values will be updated for that particular class. Then you will also update this Taylor series for that particular class itself, and that output should be such that y1, y2, y3. Suppose there are three classes, so y1, y2, y3. The output should be such that if it belongs to y2 class, the y2 class should. That is the purpose. So maximum value may be equal to actual class, like it is plus 1 minus 1 only. If it belongs to that class, ideally it should be plus 1 and remaining classes should be minus 1. But it doesn't happen if that ideal is the case. So maximum value, whatever comes, we are taking that as a value and that as a class. So that is the whole classification algorithm that we are doing here. And So if you look into yesterday, I talked about how does it relate to a neural network, right? So we are applying a kernel matrix, adding a linear layer at the start, then we're applying a Taylor series. So essentially what we're doing, we are replacing a neural network with number of Taylor series and 10 Taylor series, and that Taylor series essentially replaces the activation functions and the subsequent weight matrices. So like it doesn't replace the weight matrices, the weight matrix will be replaced by kernel matrix. It can replace as in the A value, as in the bias value of this can replace a weight matrix per se, but the remaining higher degree order terms cannot replace. So what you can do, if the model is not complex enough, you can try increasing this SV values, as in the size of the kernel matrix, you can try increasing. Or second thing is that you can add more layers of such, and kernel matrix and Taylor series, then again kernel matrix, then again Taylor series. So this operations you can increase, it will be computationally exhaustive. Or third thing is what you can do is add convolutional and max pooling layers here without ReLU function, because ReLU function, if you again apply, you cannot get this value, because there will be as in some function will be again approximated at that end. So you cannot get the exact function of mapping. For omnis,
Sir, excuse
yeah,
me, sir. I have a doubt. Uh, so, sir, like
sure.
basically, we are like the system is replacing the activations functions with the Taylor series, right?
Yeah, accurate functions with the Taylor series, yes, without the linear embedding, because
Yeah.
linear
So, like,
operation will not change the degree in the data set. Yeah,
yeah. So, like, the neural network will not be having any activation functions for that. It will be just kernel, then the Taylor series, kernel, and the Taylor series, right?
yeah, kernel and the Taylor series, because this higher order terms, whatever. So if you have seen that video by Seron Academy, what does activation function exactly do with subsequent weight matrices? Are basically it approximates the higher order nonlinearity in the given term, because if it is linear, then all the weight matrices whatever we're applying will be accurately like assuming the boundary of segregation, whatever the problem is. But if it is of the higher order, then you will have to approximate that function. So you will have to go into details of what exactly universal approximation theorem is. And Seron Academy has like explained it quite brilliantly. So that's why emphasis was given was like, to watch a video. You can watch it later as well after this. So it basically sums up the activation functions, and that activation, summing up that activation function basically approximate what exactly the boundary of segregation is for classification problem, or like as per the application requirement. So that essentially
So, sir,
we are changing by a Taylor series.
sir, one more question, sir. So,
Sure, please.
the input matrix that we will be calculating with the kernel, so will be the inputs
Yeah.
that are fed to the neural network, right?
Yeah, the same inputs. Like conventionally, we are using convolutional neural networks. So whatever convolutional layers and max pooling layers we're using here after, right? Without ReLU, we can use here without ReLU, because if you can use ReLU as well here. But the issue will be with using ReLU, then again Taylor series will have a loss of information, and Taylor series will not be an exact mapping function, because some function will be mapped by the ReLUs used in it. So if you're getting,
Yeah, got it, sir.
yeah, and that loss of info will be also like you're not it will be not different, it will be different for different classes, right? If you use ReLU, right, then it will be limited to that particular class. So why exactly you're using ReLU? Like you're passing all the 50,000, then you're using ReLU, because in ReLU there is loss of information, and then it gives an idea to a neuron, like which neuron to activate given this vector, as in which feature space to activate, which neuron to activate given this. Activate as in it will be having a non-zero value, and remaining will be neurons will be having a zero value. In that sense, I'm saying, as in remaining at least the vectors value will be zero. So that's why we don't have a ReLU here. We don't have a selection criteria. That's why we have the number of Taylor series or number of these steps equal to the number of classes. Hope this is clear. This is all our like theory explanation. Like I hope this is clear totally. And if you want to increase the model complexity, there are like many hyperparameters tuning. So we have added a C function as well. So since Surya is aware about what exactly is a lambda function or a C function that controls the margin of a support vector. So here we have not drawn a support vector exactly. So this support vector or this linear embedding will be essentially controlling the support vector. So we have not shown that here. Actually, the support vector is the distance between this and the so whatever boundary of segregation is the distance between this, as in there will be one more boundary here, which is this, one more boundary here, and the distance between this and this and this and this should be like a minimum in that sense, and distance between this and this is called as margin. So that parameter also we can like hyperparameter also we can tune in here. So that is one of the hyperparameters. It is introduced in the regulation function here. So that hyperparameter, the number of support vectors is the hyperparameter. The degree of the Taylor series is the main hyperparameter here. So you controlling this, and second, like fourth hyper parameter is like for increasing the complexity, you can repeat this kernel Taylor, I like that you can repeat. And there are like other models you can introduce conventional neural networks. So hope all the theory is clear. We'll move on to the. We just have 4 or 5 minutes. Like we'll try to cover the code in that. So first thing, the code is implemented for any data set, and whatever accuracy you get for like hello.
Yeah.
Hello.
Yeah.
Hello. Yeah. So there is a background noise. So let's ignore that. So we have implemented for MNIST data set. So these are all the imports that are done. Okay, done in a like a well scripted format, so you don't have to do that 1 2 3 what we did yesterday, like the for amplitude encoding. So this is done for the test data as well. So basically this does what it does is basically converts that IDX to NumPy format. Then after that, yeah, we are normalizing it, flattening it, normalizing it. We're basically amplitude encoding that, and this rounds up this code. Then the main code starts from here. So if you look into, this is our class of kernel. This is our class of single class. As in single class, this is repeated 10 times as of the number of classes, how many number of classes we have. So this is one of the like you can say variable here. A degree is a variable. Lambda regulation parameter is a variable here. That variable is incorporated in the like the loss function regulation. We'll look into that. And this is about point A. This is the bias of the Taylor series, and these are the coefficients of the Taylor series. So coefficients of the Taylor series will be how many? The number of degrees plus one. So that's why this is. And if you are going to higher order, higher degrees, then this code basically gives a NaN values as the outcome. So you have to incorporate that log terms, and where you have to incorporate that log terms, you'll look into. But this is the basic like the variables in the code. So these are basically the instance variable. So this forward approach, what you are doing basically for a single class is this is a theory written here. You can go over that theory. Same thing what you were explaining. Operation what we did is multiply our input vector. So this is operation is taking place in batch size. So this will have a batch size, comma the input dimension size of the vector, and this will be our support vectors because which is initialized to this value. So input dimension and the number of support vectors. This is again a hyperparameter here. So this is initiated like this operation initiated. Then we are basically we know what exactly is the Taylor series. We are having powers of that x minus a square, right? So this is done here. So elements of k, basically the elements of the vector k in the batch size, comma input dimension we are having, right? All the elements of a particular vector is subtracted by self dot a, and this is again trained by backpropagation. So this is the operation, and then we are initiating the vector batch size, comma vector to a zero values, which will take the values of whatever after Taylor series expansion operation will take, as in this. So we are adding the Taylor series, right? As in if you know the Taylor series, we already written the Taylor series. It's f of a plus x into x minus a into f dash of a. So instead of f of a and f dash of a, we have taken that as a coefficient, and we have not divided that with a factorial value. So we have directly taken that as a variable itself. So these are all the variables, and this accounts for the dividing by that factorial term as well. And then at the end operation, we already said that we are since our output is of the single dimensions, we are taking it as a sum. So we are summing over that operation, and so to get a single value. This is for a particular class forward approach. Then this is again another class which is called as a Taylor classifier, which has the variables of all this. This can act as a child class of that parent class. So we have again taken the same kernel series class here, and then it is repeated for this number of 10 number of classes. So the same operations are repeated, and the forward approach is this. We are concatenating all the y values what you are getting for that particular vector, and then batch size comma vector will be the size of this for first operation, or first as in sub batch of the epoch, if you're getting the first batch of the epoch. Okay, this is the train model then. So we have taken the criteria as an entropy loss directly. So what will be the entropy loss? Entropy loss will be the difference between, so all the values, uh, what will be the ideal y value will get if it is of the class 2. If you have three classes, it should be -1, 1, and then -1, right? So those values will be like this. You can initiate a hinge loss as well here. That will be criteria of reduction in the like loss function. So and the same thing is done. So this is a training group. So in that we have taken the batches of the train loader, and then criteria is this. Whatever score the labels whatever you have, we are minimizing that loss function and the cross entropy between between that. So cross entropy you already are aware with that formula, right? Y into log y into -1 minus y into log y, or +1 minus y into log y. That is essentially the cross entropy function here, and it is optimized. So what you have to do here, this code is working fine for okay, and then there is an evaluation criteria, so it is done for the test vector as well, and then like we are getting the test accuracy whatever it is. So this is essentially the code, and remaining are this optimizations. You can this is optimization done for specifically this laptop for increasing the efficiency, but that will be different for your end. So you can try removing this code and then making the changes in the code. But the first thing what you have to look into, so we'll get back to what are hyperparameter. First thing what you have to look into is for increasing the hyperparameter of degree. This if you'll go into about 10, 20, 30 value now, that will result in a nan value. It will explode essentially whatever values you'll get. So to avoid that, you can incorporate a log values here, as in you can incorporate if it is raised to term, right? Raised to term, as in the higher order x minus a raised to 100. If it is exploding, then what I can do is take the log. I take the log here of every expansion term, take it in the further, and then take its exponential. So log and exponential will be cancelled. Essentially, that is the point. You can try incorporating that here. Like exactly how it will be, you can try on piece of paper and you can go through that. Okay. And if you have any doubts, you can message me as well. So you can try like changing the loss function as well. After that, the main thing that comes here into picture is parameters. So how to, like, we have taken this, you already know, like Surya must be aware what exactly is the margin. So distance between the two support vectors of a particular class separation is called as a margin. So this C value, which is incorporated in the this uh, okay, which is incorporated here. Just give me a sec. Okay, okay. So it so happened like this is we are using a cross entropy, right? I'll show you a code where a hinge loss function is used, and in that hinge loss functions we are introducing a regulation term, and in that a lambda regulation term is used. So essentially here I have changed the cross entropy term, but like I have not removed. So for all the C values, you'll essentially get the same accuracies. So no need to do this for all the C values. But like I'll try to send a code today. It will have a hinge loss function in it, or below also it might have a hinge loss function, like for other data sets you can go through that. But this is essentially one of the hyperparameter which has not been implemented here. The second is degree. So for the range 2 into 10, so like we are trying it for all the degrees. Yesterday from yesterday's discussion, we already know that degree of our MNet data set is 3. So like we are trying from the range of 2, but for higher order, like which whose degree we don't know, like we will have to try an error only like this. But if you look into conventional Taylor series, the higher order terms, since it has the higher factorial terms in the denominator, so those higher order terms are essentially neglected only after 10, 20, 30 degrees. So essentially that is the thought process incorporated here. So the maximum that you have to go up to, I think so, is 100 degrees, but you can try incorporating code for higher order terms as well, like 300, 400 degrees without causing the non error. So that will be your first task. And the remaining tasks I already mentioned, you can go through that. And so this is fine. This is fine. This is one of the hyperparameters. This is one of the hyperparameters. The number of support vectors is one of the hyperparameters again. So you already know that the size of the kernel matrix is nothing but the hyperparameter introduced here. And thing from you guys. So what essentially we are doing here, essentially this plot is about we are initiating an edge. That edge is ranging from 0 to 1 and it has a spacing of 0.001. So what it will be, it will be your x-axis essentially. So this will be your x-axis and then you'll apply just Taylor series on that. No need to apply the kernel matrix at the start, no other operations as well, because the kernel matrix we know already is just a linear embedding, so no need to apply that. We're just applying a Taylor series. So here if you look into what we are doing, just k instead of k we are putting in h, and whatever a trained model we have of our CLF.a, we are doing that here. Okay, and then we are repeating, we are adding that all, we are getting the expanded term, and that will be our output plus by. So this output we are plotting on the y-axis, and on the x-axis we are plotting h. So that essentially is our mapping function. So this question without ReLU that you don't have to take. This essentially will form as the mapping function itself with a linear matrix. So that matrix can be that matrix will not affect the degree of the dataset. It will just change the coefficients of this whatever equation we have gotten or the degree of this equation. It will not change, right? It will change. It will cause like this some kind of zigzag kind of shape. But this shape, if we look into, these are like it was greater than zero. The equations are called like one is positive, one is negative. If you look at are called. So let's just see downside. If it is yeah, nah. So I have commented it out. So it will not be here. Let's check other like I will have here somewhere. Yeah, I'll show you how it looks like. It will not be for MNH dataset, I think. Let's see. I think it is. Exact functions in this is fine. Yeah, this is for the test, and this is the same code. Yeah. Okay. Yeah. It will be 10 plots per class, like per class single plot, and 10 classes 10 plots you'll get. How many classes will increase, that many plots you'll get. So you already know how to increase the model complexity, and I think so this code has the hint laws incorporated in, so you can have a look at it as well. I'll share you the code. Essentially takes the lambda regression term into picture, and this essentially controls the margin of the support vector. It is not incorporated in the cross entropy term. And the downside of this approach is it will give a threshold accuracy of 98.5. The conventional maximum accuracy of MNIST dataset, if you look into online, is 99.5, 99.6. So it's not beating that. It's beaten by 1%. So that 1%, I think so, it will be covered by the conventional filters what will be applying plus the max pooling layer, or you can try increasing the model complexity. That is the second option without incorporating any kind of activation function. So you already are aware of your task. So hope this is clear. If you have any questions, you can text me or you can ask me. Please go ahead.
So sir, like I guess you might have answered this question before, but just to be sure, can you
Yeah.
just give us a quick uh, like, points of what tasks we have to do, like me and Zipper?
Okay. This has already been written here. You can go through like what we are expecting from like you. So the hyperparameters. So first is tuning of the hyperparameters. You can try tuning in the hyperparameters and find other approaches that doesn't need to load all the data. Like we are just using the for loop, and then in the for loop, what you're doing is trial and error approach, as in putting in all the degrees, then taking by application, calculating all the values, and then finding the optimum parameters. So instead of that there might be some alternative approach. There might be like you can decrease the size of the data set, first fine tune the model, and then increase the size of the data set. That approach can also be tried. So that is one of the approach for this data set, all the 4 data set. Then what you can do is, as I already discussed, the decrease of the data set are limited to 10. After 10, you will result your code will result in an error, because the loss, as in the values, uh, means the initial values, whatever initializing your kernel matrix, and then whatever initializing a Taylor series, that decrease will account for a value of the loss function that is so high that will cause an error. So to avoid that, like, you can think of what changes can be done, what regulation techniques can be used. Apart from that, what normalization techniques can be used in the parameters that we are initializing. So that is one of the tasks like you can do in this. And then you can incorporate the conventional and the conventional filters and max pooling layers here. That is the third task that you can do, and you can go through this 4 approaches. So if you'll get the first approach, this first approach you've gotten, the remaining approaches are similar. Like I don't think so there is anything special that SVM kernel taken as a Hamiltonian, and then I got, so this approach has not been implemented. You can try so this approach is yet to be thought out, so you can try remove this. The SVM kernel matrix taken as a density operator, and then applying unitary evolution in batches and complete matrix. Okay, so this operation is also like you can try, you can like you can ignore, because what exactly so this can be done in terms of Fisher kernel. So Surya, you might be aware what exactly is the Fisher kernel, right?
Yes,
So
sir. I do
Fisher
have a
kernel,
little
are
bit
you
of
aware
idea.
about? UK dagger, that equation what you're doing, that is comes from the quantum information theory. So that essentially what we're doing in this is we're applying a unitary of transformation to the kernel matrix, the conventional kernel matrix, not this kernel matrix. The conventional kernel matrix, what I will be doing is x dot linear kernel matrix, x dot transpose. So that dot product between x and all the remaining x's, that will form a Hermitian matrix, and then transformation of that using U dagger will result in an output kernel matrix that will be linearly separable. As in, you can find the optimum alpha values from the dual Lagrange equation, and then like you can linearly separate that to the class levels. So that can be also incorporated, but the main focus should be this first. Yes. As in, if you can increase the accuracy at least by 1% and reach it to the state of the art of MNIST dataset also, that is also fine. As in, instead of by using the 4 5 techniques we already discussed. Okay. And the last technique as kernel matrix is Hermitian, only taking the upper diagonal. And this is again a thought process. No need to implement this. We can research on this later. But this is the main problem statement. And the same thing has been done for all the remaining 4 datasets. So you will find the code is little bit bigger, but you will find the code like everything is similar. Only one approach is differing, that for double labels for PCAM dataset, but you don't need to go into that detail. This code also works for the PCAM dataset, so you can ignore that code as well. Okay, fine. And if you have any doubts, you can ask Aslan. Okay, yeah, fine. Any more doubts you have?
No, sir. Everything is fine.
No, sir.
Okay, okay, cool. So I'll try to share that hinge loss code with you. Yeah, which has lambda as a parameter, as in 1/lambda is nothing but the C, and the C controls the margin. So I'll try to share that code with you. Fine. And so these are all the, so at the end you can look into, this is type 2, and these are the thought types. So SVM linear kernel taken as a density operator, then applying the unitary evolution. This is already been written here, you can try reading this. Then the fourth is as kernel matrix have you can ignore this. So fourth, second you can ignore, third you can try incorporating, and remaining code you can try ignoring. Only the first block is important to you, and the 4 5 tasks, like whatever you discussed. Okay, and this yeah, so this is again a type of subtype of type 1 itself. So here you can share the linear kernel at the start. So what we have done, we have not taken the we have taken the trainable kernel matrix, right? We have multiplied with the input vector. So instead of doing that, what you can do is linear kernel first. We can operate that. We can get a Hermitian matrix. Then we can do a UK dagger, and then we can some more dimension one. So if you understood the start point, what I started with, similar fashion this is written. So what exactly linear kernel operation, you'll know it gives a Hermitian matrix. UK dagger will perform operation on that kernel matrix, it will result in an output matrix. And then if you sum over dimension one of that, you will just get a single value for that particular data set. And like you can classify it to different labels. So that was a thought process here. And the type 2 is this. So I have not written that, or oh no, so below that only, these are fine. You can try incorporating this, the fifth type. But below that only, like you can try shared kernel matrix. So we have taken different kernel matrix for different classes, right? You can try a shared approach, as in shared kernel matrix for all the classes. You can try shared Taylor series for all the classes, but you'll find that the accuracy is not yet subpar, due to the fact that we already discussed a ReLU function essentially activates or deactivates a neuron. So it's not done in this case. So if you'll incorporate a shared kernel and if you'll incorporate a shared Taylor series, do that. So basically the accuracy will be reduced, and if you try to incorporate both the shade, it will be equal to I don't know, it will be equal to, it will be subpar. You can try incorporating that as well. So hope this is clear.
Yes, sir.
Yeah, okay. And one more thing, like you can try incorporating other kind of encodings. I don't think so it will be that much affecting this, but we have tried amplitude encoding here. You can try other kind of encodings. So basically, Taylor series demands the values to be between 0 and 1. So that should be kept in mind for initiating your x vectors or your input vectors of the image. So that's it. Yeah. Okay. Fine.
So, sir, like we can use other type of encodings, right?
Yeah. You can is like use other kind of encodings. All the vector encoding incorporating unitary as well, but null density matrix encoding, I think so you cannot here. That needs a further research, because you see it is per se a matrix form. So like and it is a Hermitian matrix. So whenever Hermitian matrix comes into picture, you have to incorporate both U and U dagger. Means two operations should be there. Like no single operation of matrix can do that job. So that transformation to be coherent requires a U, K, and U dagger, as in U and U dagger on both sides. So you can try researching that as well. If you can come up with a suitable architecture, that is also fine. But the main research topic should be your type 1, your type 5th, and 3, 4 types that we discuss, subtypes in that.
Yeah, okay, sir.
Okay, okay, Surya, okay, Siddhant. Like we are expecting good results from you guys. Like especially Siddhant has written like quite a good notes about Taylor series, like where it can be used. Like there is a wavy nature at the end if you'll increase the number of degrees. So like I'll be expecting that to be incorporated here as well. So kindly go through the code in detail and let me know. If you have any doubts, you can get back.
Sir, like, is there any kind of deadline where we have to show you something, or it depends on how fast we solve the problem?
No, there is none. There is none. Deadline is the deadline is up to you. Like you can take 1 month, 2 months of time, because it's up to you, because you are either a student or you are either a working, like working somewhere. So it's up to you how many days you can give to this problem. But before, like you should at least complete the problem statement. This problem
Yeah,
statement and your common task.
yeah, yeah, got it.
A deadline, if you'll ask me personally, is 2 or 2.5 months. You can extend that period of time. And if you'll find if you will find your work good enough, we can extend that further as well.
Yeah, yeah, got it, sir.
Okay, Britan, can we move on to the next session? Hi, Britan. we forgot to discuss the uh, Sukrikant had left a meeting. So hi Sai and hi Sweta. Am I audible?
Yes, sir.
Okay.
Hi,
So
Abhishek.
without any
Yeah, you're
further ado,
audible.
like uh, yeah. So we are already 20 minutes above the time allotted. So we will begin. We are going to discuss now QSVT, the task allotted to you guys. So what exactly the task is about? That will start. So yeah, is my screen visible?
Uh, Not yet.
Okay. Okay. Yes. I think there is some issue. Okay. Yeah. Okay. Some okay, there is some issue with screen sharing. I have shared my entire screen and still it's not visible. So I don't know what's the error. I try to share just the window. Okay. Uh, yeah. Sorry guys for the delay. I'll try to reconnect by disconnecting because I'm not able to share this.
Hello, hello, hello. Can you hear me? Sai?
Yes, sir. Yes, sir. You are audible.
Okay, so
Yes, yes, Navneet.
so is it fine if we like extend this to further? I mean, because the plan was to complete it by 10. So is it fine with you guys?
Uh, it's fine with me.
Akshay, can we finish this within 10:30?
Yeah, yeah, sure, sure. So sorry for the delay. Like it got disconnected in between, and like you were also not available, so I was not able to join as well.
So
Like you are
Sweta, is it
disconnected.
fine with you if you can wrap it up by 10:30?
Yes, sir.
Okay then, Akshay, please go ahead.
Yeah, sure, sure. Um, yeah. Hopefully my screen is visible now. Okay. This is the code for quantum singular value transform. Before doing that, we have a doc ready for it. So bear with me. I have to search for this. Okay, okay. Yeah. Uh, yeah. Sorry for the sketchy figures as well here. I think it will not be clearly visible to you guys. So I'll just give you a brief overview what exactly is the QSVT, and then we'll move forward with what exactly are the architectures mentioned in the code via theory first and then via code. Okay.
Okay.
Okay. If you have gone through the code, it is the first line is written is QSVT is the only quantum algorithm for now which can incorporate nonlinearity into the picture as a nonlinearity into the incoming data set by increasing the number of qubits. So this is one of the main algorithms because all the quantum algorithms are linear without. So that's why like if you are able to classify or get the state of the art accuracy using this for MLE data set at least that will also be a goal achieved. So without any further ado, this is different, totally irrelevant. I'll just explain the circuit from here. So this is our circuit, a general QSVT circuit. What a general QSVT circuit does is basically it has a one QSVT qubit, it has one ancilla qubit. So pardon me, this is not the circuit we have implemented or we are like planning to discuss here. So this is the circuit that we are planning to discuss. So ignore this block, ignore the end block. So this is your first is your QSVT qubit, which will contain the Hadamard gate at the start, and then control X rotation gate, control X gate or C naught X, basically CX gate, and then a rotation gate, which will be parameterized by of the angles of the quantum angles, which will be parametric this rotation gate 10. We'll get back to details of what exactly those values are, but this is your circuit. So QSVT gate is the gate that applies a nonlinearity onto the unitary matrix. So how it does exactly does that. So what is the equation that we'll be getting after this? We'll discuss that as well. But this is your classification qubits. It's recommendation qubits written here, but this will be actually your classification qubits. This unitary will be parameterizable, or it can be your unitary of separation or unitary by ML, what we discussed in our previous session, like the first session, or it can be unitary by QR approach. So we'll go through the code, we'll understand what exactly details of the implementation are. But bear with me for now. This is your circuit. What it basically does, it applies a polynomial equation transformation of the matrix. So if it is essentially a classical situation, then what it will do is basically it will apply this kind of equation. I don't know where it's written. This is quite an old GPT, but yeah, classically it will apply this. Yeah, so it's written. Classically, it will apply this. So what it will does is that circuit essentially will apply a polynomial transformation on the matrix. So as in, what it will do is it will take whatever degree we have, it will apply a degree on that that matrix. We'll divide that with the maximum element so as to preserve it in between 0 and 1. And then you'll add it with the b raised to d minus 1 and so on. So b is essentially the classical matrix. And then we have discussed the unitary encoding, right? So you'll be unitary encoding this classical matrix to that that unitary encoding. So that unitary encoding. So this is essentially like the only things that I wanted to discuss. This is totally a separate document, so it is not relevant to whatever we are planning to discuss. Only the circuit of the QSVT is universal. It will remain the same irrespective of the application. So this work has been done by me, but a different organization. So this will not be a work we'll be doing here. Okay. So moving on. Like this is a general circuit again. So what essentially it does is basically it applies a polynomial transformation. So like how exactly we are parameterizing that it is given here. So instead of like having, so you know that yesterday, right? What exactly is a unitary matrix? Essentially this is our X matrix. It's represented in a scalar from here. Then this will be root of I minus a dagger. This will be root of I minus a dagger a, and this will be minus a dagger. So this values, whatever are written in terms of matrix form, you can write in terms of singular value forms here. And whatever operations we'll be doing with the help of gates, those operations will be performed on this matrices, this is scalar values, and this scalar values will undergo polynomial transformation where you're planning to implement it on an actual quantum hardware or quantum algorithm. So this is the like equation. So what you're doing is this basically descaling the entire matrix, the polynomial transformation of entire matrix on just the 4 values, whatever you are planning to parameterize. So what this X values represent, this X value will be the eigenvalues or the singular values of this A value of this A matrix, what you are trying to write, right? A will have a SVD decomposition, right? It will have A, B, C transpose as SVD decomposition. We will be eigenvalue matrix of that. That eigenvalues will essentially be X here, or that SVD values or the singular value decomposition matrix values will essentially be X here. And that transformation, this rotation gauge will be parameterized using this equation itself. And this like transformation of the rotation gates, parameterization of the rotation gates will be applied on this, and essentially what you will do is this equals to a p of x, a polynomial transformation of x. So you'll get you will be applying essentially for this case the equation which will be seeing b raised to 9 plus b raised to 8, that equation we were seeing, right? B raised to d, 1 upon b raised to d, element of b raised to d into b raised to d plus 1 upon b raised to d minus 1 into b raised to d minus 1. So that essentially what will be here, you will be substituting instead of b here x, a singular value here, and then like you will be applying a polynomial transformation of that. That is essentially the purpose of this algorithm. So it incorporates non-negative on the eigenvalues or the SVD values using this circuit, and that is what is put in the paper of this. When it first came into the picture, essentially it was a unified kind of framework, unified algorithm which can essentially you can incorporate any algorithm, whether it be Grover, whether it be Shor's, or whether it be any quantum algorithm that is possible in the future as well using this technique. That was the sole purpose of developing this, a unified framework for like incorporating any quantum algorithm, and it incorporates non-linearity as well. So it serves our purpose. So coming back, this is all the theory that I wanted to impart. Coming back to our implementation, only the theoretical concepts. This implementation for this case is totally different. It's not related to our project. So kindly ignore that and ignore the logo here as well. So please. Uh, now, like whatever we have given here in the document, it might not be clearly visible to you guys, but it's the same circuit what you have seen. Only instead of like we have kept this box as a blank previously, now it has been like quantum encoded. So at the input, these are the classification data qubits. You already know how to quantum encode from the yesterday session. You will be putting quantum encodings, various kinds of quantum encodings here, and then this is our QSVT qubit. Whatever you discuss, it will remain the same, and this will be our ancilla qubit. So ancilla qubit essentially is the qubit just for increasing, just for getting that. So after unitary encoding, you have that increase in 1 qubit, right? So that's why 1 qubit should be increased here. So that's why ancilla qubit we're incorporating. And the second thing is that you have to apply this transformation on this qubit as well, right? So that C naught should be entangled, that this qubit, QSVT qubit should be entangled to this ancilla qubit. So that's why we're incorporating a C naught gate here. And this essentially can lead to a even and odd polynomial transformation on the singular values of the classical data matrix. So hope this is clear. Now coming back to our implementation, this is all the theory. Even if you don't have a clue about theory, just remember that it can incorporate non-linearity into the equation. That's the whole thing. Now, since this is quantum inspired algorithm, we have just taken this as a 4x4 unitary matrix. We'll come back to the implementation. You'll get a clear-cut picture. So these are so tasks are written in the comment section. If you have any kinds of doubt, you can ping us. So you can go through the task, what exactly your task will be. So this is our like all the things which are discussed yesterday only. This is nothing but the data pre-processing, and we have incorporated quantum amplitude encoding here. So yeah, and this is done for the test data. Okay, the same thing first. Now this is our first architecture. So in the first architectures, we have taken as parameterizable unitaries. Parameterizable unitaries means what exactly? If you look into the figure, or if you look into this document, okay, this unitaries, whatever you are taken, right, unitary of separation, these are parameterizable unitaries taken here. Baki the architecture remains the same, but these are parameterizable unitaries. Okay, now coming to the implementation, necessary libraries are imported. So this input vectors are nothing but your input pre-processed vectors, as in amplitude encoded vectors. These are, so this will be of the dimension 50,000 comma 64, and these are your pre-processed vectors, as in if you look into this 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 is the vectors, and you have like converted that into a tensor format. Okay, and the second thing is target states combined. So target states combined we have already discussed yesterday. Like since this is a 64, an ideal implementation of that will be equal spacing. So we are equally spaced that, and that equal spacing comes out to be 7. So it is 0, then 7, then 14, and then in that range. So this is our target states. Now this is again the implementation of custom reduce aileron pad2, because we cannot go below the minimum learning rate of 1 e to the minus 50. Hence we are implementing this, but you can remove this and you can directly implement reduce RL from pad2. That is also fine to the scheduler. It will control the learning rate, but it will not go below 10 raised to minus 6 or in that range. Now this is our first class, like the matrix model. So what essentially we are doing here is you can control this range. So what essentially these are nothing but the rotation gates. The rotation gates which we are applying here. The rotation gates. So this rotation gates, pardon me, This line which are drawn now, this is wrong. This is not there. I have shared the similar thing with you guys. This is not there. I'll share the updated architecture in a screenshot format with this guide, which we saw in the presentation, right? That I'll share. So this is not there. This is just a 2x2 unitary matrix, and those are all parameterizable we have taken, as in the values are all parameterizable. Unitary constraints will be there. Hence, from yesterday's discussion, it will be n into n plus 1 by 2 only, as in the number of values that can be exactly independent of each other. So only 3 values we can control out of the 4 values, but we have taken all the values to be parameterizable, and such that unitary constraints also imposed in that. Okay, so this is our 2x2, and we have taken repeated that 26 times. This is one, this is one, this is one, like this we have repeated that to be 26 times. Okay, hope the first line is clear of the code. The second line is what? These are nothing but our FC layers. So this is nothing but our unitary matrix, and this is parameterizable unitary. So if you look into we have our this value to be 26, right? Sorry, this value to be 64, right? So to account for the ancilla qubit, as we are entangling the QSVT qubit with the ancilla qubit, the architecture is designed in such a way only. We are not changing the architecture for the start. So this we are taken to be 128, as you can look from the figure as well. So this figure. So the unitary of separation, it's up to here, as in, right, it incorporates the ancilla qubit as well. So that's why it's increase in 1. So 2 raised to, we have taken 1 dimension to be extra. It's first classification qubits are just 6 here. We have taken 1 qubit extra. We have taken 2 raised to 7 cross 2 raised to 7 in the dimensions of the unitary. Just a sec, my laptop is, yeah, okay, still hanging. Okay, yeah. So this is our unitary, and it's repeated for 25 years. Okay. If you look into architecture, you will find that it's written U into U dagger. It's written U, then it's written U dagger. But since we are making it parameterizable, we do not need to do that, because parameterizable, as in type program itself, will decide what are the values. Will not be having any say in that. What we'll be having say in just the loss function and whatever output we want. That is the target states we want. The criteria will be decided between the target states and the output which we got from this circuit. Okay. Yeah. So
And
this is fine. Now,
uh, actually,
yeah,
just a
yeah,
small
yeah.
question.
Please. Sure.
What is the 26 times? Maybe I lost it
Yeah,
somewhere.
this is a hyperparameter which you can control. This 26 is nothing but how many times you're repeating this. So you have seen that the b raised to d we are taken, right? D. B raised to d plus b raised to d
Yeah.
minus 1, that equation that. So that degree d is
Mm-hmm.
controlled by this. So essentially for degree 27, you are incorporating this 26 values. As in what it will do, it will apply
Why we
polynomial
take it
transformation.
26?
No, you can take any value. You can start with 3. You can start with 4. You can
Okay,
start with any
okay.
value. You will take it as one value, it will be
Got
just
it.
linear. Yeah.
Mhm. And one more doubt. Why are we applying this Hadamard gate? Even yesterday also I have seen. Why is the first gate always Hadamard? Is there something like it's the first gate or some
Okay,
only
yeah.
specific to
So I
this?
had researched that particularly here. Yesterday was totally different case. Here it is totally different case. So yesterday what we were doing is basically, uh, so yesterday if you look into initialization of the qubit, what happens is you'll get the vectors in the format of, just give me a sec. My mouse is having some issue or laptop is having, I don't know. Okay, here. So yesterday, if you look into what was happening basically was, yeah. So yesterday the initial, okay. Okay, so the start value was 1, remaining all values were 0. Just give me a sec. Try to close unnecessary things. Okay, yeah, that is performing better. Okay, still it is, yeah. Okay, so in yesterday's case, what we did was, Yeah. Yeah. So in yesterday's case, what we did is 100 we are applying right at the start. So this is our input qubit state. Okay. So this is our input qubit state. Let's assume it's just a okay, just a 2 qubit state 1000. So this is our input qubit state. Now, if you'll apply a unitary here, as in you will take any matrix here, whenever you perform a matrix vector multiplication here, right? What it will do is basically I'm just taking for simplicity case is to be Hermitian as well, and it should have a unitary constant as well, just for simplicity, and remaining factors will be same. Remaining this will be element, like some elements. Okay, not an issue. But when you multiply this vector with this matrix, what it will do is basically it will take this first column only. It will not take this remaining elements. But what your image features are, this whole matrix is basically your feature matrix, right, for that particular image. So that selecting only this starting point as your vector will result in low accuracy or any random accuracy. So for avoiding that, you will have to initiate this to all ones. So that is done by a Hadamard gate, as in initiating this to all ones, then applying a probability amplitude here for normalization, 2 raised to 4
Mm.
or 2 raised to 2 in this case. Okay.
Yes,
Yeah,
yes, yes.
it,
Got it.
it is it, yeah, yeah. So this will be some addition cases, and some minus sign will also be here because Hadamard has a minus sign. You can go into have a look at it, like what exactly this vector is, but there will be ones only here. Okay. So that is why we are
Sir,
incorporating Hadamard. Yeah, yeah. Please go ahead, Shweta.
I have a question on circuit you showed.
Okay, yeah, yeah. This circuit or in
Like,
the presentation? Yeah.
no, this one only. The Hadamard is taking the state to the superposition, like plus state or minus state,
Okay,
and we
okay.
are acting
Yeah.
control X on it. That it means if the ancilla qubit is 1, then the X will be applied. So on a plus or minus state, the X will be behaving like Z gate. So
Yeah,
we
yeah,
are
yeah.
just
That's true.
applying the phase here, and after that we are again rotating, and we are applying phase and then rotating. I don't understand why are we uh, applying phase and rotating as well.
Okay, okay. So if you don't understand this per se, like I didn't plan to discuss the theory, what the
Okay.
theory is explained in detail in that document, the PPT, and this was implementation done by me only. That was 7 8 months back. So if you have to refer the theory, there is one paper by Chuang, I think. I don't remember his name. But there is one paper of him in 2000 recently only 2018 or 19 something. You can refer to that. It explains clearly why this circuit incorporates or implements a polynomial transformation of a matrix. So if you remove this Hadamard, right, particularly the question asked by Sai, if you'll remove this Hadamard, right, that can also be done, but it will implement a polynomial transformation of the matrix that will be different from what you are trying to implement. It will be just odd and even terms. So there are like 2 3 points here. Like if you'll not repeat this at the end, that will be an even implementation like that. And if it will repeat this, if we'll remove this edge, that will be an odd implementation. Something like that is there. The details need to be checked once. Like I had done a thorough research in this doc, but I felt like this is a general approach because will not be like limited to rotation gates here, which will have just the 2 parameters which was taken in the initial paper. So like this was the general circuit that we came up with. But if you want to go into details of that, I'll try to share the paper and two YouTube resources. You can have a look at that, and you can come up with a new architectures as well. So using the implementations what we have done, you can come up with your new implementations or new architectures and like try to incorporate the classification algorithm there. The remaining things will all be same. You have to just change 2 3 lines. That will be the only change as per. So if you want to remove Hadamard gate, you have to remove that Hadamard gate from there. That's it. No, that much changes will be there. The main thing was implementation of this using the classical library that we have already done, and like the architecture that we had come up with. So like the accuracy, if you ask me particularly of this algorithm that we have implemented is subpar only. So that's why I like, but the as per whatever scientists have researched on previously, and based on their context return, this this is the only quantum algorithm that can incorporate non-linearity into the picture. So if we can show in advantage or quantum advantage, it should come from this algorithm, because it is such an algorithm based on the rotation gates that we will train. It can incorporate any quantum algorithm, as I already explained to you. Grover, Shor's, whatever it may be. But it might happen the circuit depth might increase, the circuit depth might increase from the Shor's and Gross algorithm what we already have, but this can incorporate it as a universal architecture of any quantum algorithm based on the rotation gates that will be taken. So the advantage, if it will come from here. That is the thought process. But anyways, so if we'll go into details of theory, if you like to go into details of theory, I'll share with you the paper.
Okay, sir.
We'll go back to the we'll go back to the implementation details. This is nothing but your start qubit state of what exactly your QSVT and your ancilla qubit state, which is the start, which is initialized as 00 format. This is your Hadamard gate at the start, that is initialized to 0.007 1 that you already know. And this is your since you're not applying any kind of operation on this, right? Since you're not applying any kind of operation on Hadamard, below Hadamard, you're applying identity on ancilla qubit. That identity is incorporated here, and this is your C0 gate. So this C0 is also reverse C0. And then if you look into, if you write the bracket notation state in this case, if you'll write the bracket notation in this case, if just taking this and incorporating all the states here, 00 if you'll write 01 you'll take, 10 you'll take, 11 you'll take, and put on this gate, then you'll find that it is not the conventional C0 gate, which has a 0 here, and it has a 1 here and a 1 here, but it has ones here. So you can put you can solve it like it's easy. 00 if you'll put in, what output will get? 00 only. If you'll put in 10, then also you'll get 10. But if you'll put in 01, then 10 you'll get, like 11 you'll get, right? So that is the only change. So you'll get this as the 11s. So okay, fine. And this is your make unitary. So whatever initializations you're doing here, these are random initializations, right? Random initializations, as in this will be a non-unitary matrices. To make that unitary, you're defining a unitary layer here, define make unitary, and in that you're applying your SVD decomposition. So whatever weight you're already having, that will be passed here. Since it is a function, that will be weight will be passed what we want to make as unitary, and then it will just return this. As in, it will remove the eigenvalue matrix. It will just return the product of these two. And this is again a decomposition. You can try implementing that as well. SVD is known to get good results, so that's why SVD is kept here. But sometimes it so happens that it doesn't converge. SVD is equivalent to the least squares algorithm if you go into details of that machine learning. So sometimes it so happens that it doesn't converge. So error also will get produced. Like in that case, you can try incorporating this QR decomposition. QR decomposition doesn't do that kind of error. Okay, fine. So moving on. So in the forward approach, what we are doing exactly, we have to get our final state, what it is, because we have to compare that with the target state, right? So that will be our aim here. So this is our HI state, as in the first two qubit, what state you will be getting is this state. So this is the gate operation first, torch, cron, the Hadamard gate, and the ancilla gate. You're tensor producting, you'll get a 4x4 matrix here. And then, so this matrix operation you already know, right? Should I explain this in detail or no need? You already know, right? If this is a Hadamard gate, there will be identity gate here. You will be Kronecker producting that. After Kronecker producting, you will get a 4x4 matrix. After that, you will multiply your input state, whatever it is here, 100 state, with that matrix, and then you'll get an output matrix here. So is it necessary to explain that or no?
Maybe once you
No.
explain.
Yeah, okay, fine. Sure. So this operation basically is your gate matrix Kronecker product operation. So since there is Hadamard gate present on the QSVT qubit and no circuit present on your ancilla qubit, so this operation basically is your gate matrix qubit. So that's why you're tensor producting this Hadamard. You have to state here as in ancilla, this state here, as in QSVT ancilla start state, your return here. You are just calling that state here and you're multiplying with. just this operation. You're Kronecker producting this with an identity operation here, and then you're getting this state. This state, 4x1 state. Once you've gotten that state, then you'll be multiplying that with the C naught operation. So C naught operation we already incorporated, and okay, yeah. So what we are doing here, current state is equal to. So now we're making that as a current state. Okay, okay. So this I missed, right? So it's taken here. So self dot c naught ancilla QSVT at the rate hi state, right? So this is your HIC state as in the state after this operation. There it is. So this is your state after this operation. Okay. So we are still this point now. Now, so after that, what we're taken Kronecker product of. So you're making the rotation gate 25. So okay. So this operation, what we're basically doing is now after getting this state, what operations are remaining? After getting this state, what operations are remaining? You have to multiply this with the Kronecker product of I first, and then multiply this 4x4 matrix with this state, right? This state, whatever state you'll be getting. So first you have to make this matrix unitary. Then you have already written that function make unitary, right? So your self dot make unitary of this rotation gate here, and then Kronecker producting that with your I, which you already like incorporated in the above initialize. We already initialized this state. This is sorry 2x2 matrix, and then we are Kronecker producting that with sorry. So yeah, rotation gate with the ancilla qubit, that is fine. Then we are Kronecker producting this with the current state that we have. No, sorry, not current state. Just give me a sec. Okay, these two operations represent the Kronecker product of this, and then after that, whatever output we'll get, that will be Kronecker producted with this state. So this is that operation, and then we are producing that with our HIC state. So hope this is clear. So up till now, we have reached till this point. We have reached till this point. Sorry, we have not taken the C naught gate till now, right? We have not taken the end C naught gate. Yeah, yeah, we haven't taken the end C naught gate. So up till now, we have reached till this point. So hope this is clear. If you have any doubts, like you can ask. So like instead of following a like 2-3 step process, you can follow 2-3 step process out like incorporate it in a single operation. So Kronecker product of first two matrices, like the rotation gate and the ancilla qubit, and then after that Kronecker production, we are making that unitary. So this is Kronecker product of that itself, and then Kronecker product. So okay. Uh, okay. Just give me a sec. Mhm. Yeah. Now it is clear. Yeah. Sorry. So this is Kronecker product, and then you're multiplying this. So what exactly this operation basically does is this. So you're Kronecker producting this operation with this identity. Once you get that, you're multiplying with the state here. Then you'll get the output state here, and then like you're Kronecker producting that with your X. So what this X is basically, this X is your input state. This X is your input state of classification qubits. So hope this is clear now. Like, is it clear?
Yes, yes.
Yeah, and still now then one operation is remaining here. We are not multiplied this with C naught. So that I think needs to be done. I think so there should be before this operation at the rate HIC, this is fine. No, before this at the rate, so before this, there should be a self dot C naught right here. I'll have to look into this details, but there should be a C naught gate here. Um, so some error here. So yeah, so this we have taken that as a unitary, we made that as a unitary. This is a parameterized gate. Then we are connecting that with the identity operation. This is fine. Then we are multiplying that with the C naught gate, right? Because there is a C naught gate. We have not taken that C naught gate in the for loop. So this
there should be a C0 gate here, and then we are multiplying that state with the state we have gotten before that. So now it is clear, I think. Okay. Hopefully this is clear. Yeah. So moving on. So now we are adding a loop. So because we already know the operations are repeated, as in operations, what will be repeated since the first operation we have done here. So this, up till now we have done, we have chronically produced this state, whatever you got with the X, as in this state is totally produced now from our circuit. Okay. Now we have to move forward with our circuit. So if you look into circuit, what operation is repeated? This operation is repeated completely. This operation is repeated completely. Then we are repeating this operation. Then we are repeating this operation. Then we are repeating this operation. As in this operation is repeated for a certain period of time, right? Is that clear? At the end also, you are ending with this. So this operation is repeated until end. So first you have to multiply this with an identity operation, like identity operation canonical product with this, and then multiply the state what you have gotten previously. That will result in an output state here, and then this operation you have to multiply, as in you have to first canonical product this with identity, and then from this, or you can multiply this all, then from multiply this with identities, and then get a matrix here, then multiply our state what you have gotten with that, and produce a state here, and this will be done in a loop. Hopefully this is clear. Like this is done here itself. So this is done here. So FC unitary, we are taking a canonical product of the ancilla qubit and the make unitary of FC layers 1. So this FC layers 1 are nothing but our unitary of separation, the measurable unitaries. And then so here, before going into the rotation gate and the control X gate, we are multiplying that with our current state, as in whatever unitary we have got, and we are multiplying that with the current state. So this unfuse operation, basically it's for matching the dimensions here. So because we are initializing with the batch size comma the input dimension, so this unfuse operation is performed just to match the just for multiplication to happen. So if you remove this, you'll get error of dimensionality. So anyways, and then we are again squeezing the state back. So this is fine. Now if you look into this, so this rotation gate, we were written it in terms of degrees. So since if you look into paper as well, we are starting with the 10th degree, then the 9th, then the 8th, then the 7th, like this at the highest degree. Then we are minimizing the degree. The last will be the just the bias term, or the just the bias term, or an identity matrix multiplied by a scalar. So to give that name, or that degree name here, we have taken this as started from the last. So this we have started from the last. So that's why. So this we are started from 25 if you look into. So we have not taken it as 0. So since we have started from last, we are doing 24 minus I. So whatever RG IDX is, basically we are starting from the last. So this rotation gates, whatever encoding, we have started from the last. So hopefully the operation is clear. Should I go into more details like how it is implemented now? Hopefully this is clear.
Yes, sir.
Yeah, it is clear, right? It is just a matrix vector multiplication what we're trying to do here. And if a gate is not present, you're doing a chronicle operation there. Same. So if there is any correction implementation of this, kindly correct it. So I have corrected this. Incorporate these changes in your code as well. You can look for look at the architecture, and if there is any mistake, you can correct that. Okay, fine. This is fine. Now, so what this code returns basically is your current state. After all the operations, at the end, it returns your current state. And that is what we require in the combined loss. So this combined loss, whatever, it has two arguments. One is the output, whatever output we have gotten from this, and our target, whatever target we are giving at that input. So one thing is that now the main thing comes into the picture here, how to index for measurement. So if you look into, these are our target states, and these are our like non-required state, right? So whatever output you will be getting will be 2 qubits extra, in the sense if it is a 2 raised to 4, if it is a 16 cross 1. Now in this case particularly, target states are of the dimension 64, so it takes 6 qubits. 2 qubits are always extra, as in the output vector what you'll be getting is of the dimension 256. 256 comma 1 will be the dimension of this. Okay, hopefully this is point clear. This point is clear.
Yes, sir.
Yeah. So to control the dimensions, as in we want just the target state. So if you write this state, so actually what will happen on the quantum circuit is basically you'll measure this. You'll measure this and then this will be a target state, right? So you cannot incorporate a measurement criteria here. So how to incorporate measurement by indexing, that's written. So what we'll try to do, we can write this state. So if we'll take it as a Z basis measurement, we can write it as 0, 0 tensor product with I'll write it on okay. So already 10:30. I think it will go up to 11. So bear with me, guys. Is it fine?
Uh, yes, sure, for me.
Okay. So this and tensor product with your remaining target states. Okay. So we don't have a control over this. Okay. So since we don't have a measurement value, what we'll try to do, we'll reshape this tensor. Okay. So output, if you look into ESD reshaped, it is reshaped in the form of 4,64. So what this will essentially do is basically it will form a 464 cross 1 vectors. Okay. It will form this 464 cross 1 vectors. Okay. As in whatever measurement value, if it is 0, 0 measurement value, you'll get this at the state. If it is 0, 1 measurement value, you'll get this at the state, like that. And normalization term will be there at the start. So some A normalization term will be there that will normalize all the state at the, as in all the state superposed state return. Hopefully this point. Now since you're not able to measure this, you reshaped it. Now what you have is just this four states with you guys, with you, because this is your position now. Now it becomes a position in your reshaped state. So this becomes a position, this becomes a position one, this becomes a position two, and this becomes a position three.
Um,
And these,
a small
yeah, yeah, please go
this
ahead.
reshaping is actually kind of classical way of doing the data. How do we reshape data in quantum system?
Okay, so that is the technique here, measurement by indexing. So if you want to, so if you look into, there is one like okay, that different architecture that is given to Tulsi, it's not relevant to you guys, but in that measurement by indexing is done. In that per se, the measurement of the middle qubits is done. So that is essentially a challenging problem than compared to this, because this two qubits are at the end, so you can reshape it accordingly. The teleportation also thing, we can reshape it accordingly. So this reshape can be done. What this reshape essentially does is this which are written here. So this state. So this state is nothing but the reshaping what you written, if you're getting the point. So this reshaping is our inspired way of reproducing whatever quantum operations are doing, as in quantum state is reproducing. If you measure your state in Z basis and you'll receive 0, 0 state, then you'll get this add state as the output. If you'll measure your QSVT and your ancilla qubit in 0, 1 state, you'll get this qubit as your output, this state as your output. Hopefully this point is clear. So this is our way of reproducing what exactly happens in quantum, what exactly happens on quantum computer after measurement. But we are not making any measurement. We are just reshaping or rewriting the state. Hopefully this is clear.
Yes, a little bit. I'll again think of it again.
Okay, okay,
But yeah, I
okay,
understood.
okay. So this is a 4 cross 1 shape, right? 4 cross 1 shape.
Yes.
4 cross 1. This is again a 4 cross 1 shape. For convenience, what we
Yeah,
are doing, we are writing in terms of 0, 1 basis, right? We're
yeah,
writing
yeah,
in terms of 0,
understood
1
that.
basis.
Just
Yeah, yeah.
about reshaping itself, I'll think of it later. But now I understood it is more or like uh, multiplexer, demultiplexer, selecting bits.
I okay, okay. Okay. So whatever state we have, right? Whatever state we have, or whatever state we have produced, that state will be in terms of addition. We have these states now, these four states. But what we assume that this position will be like given to this. zero position will be given to this state, one position will be given to this, second position will be given to this, third position will be given to this. This addition is not incorporated here.
Okay, okay,
So
okay, got it. Yeah, now I
yeah,
understood.
yeah,
Okay.
okay,
Uh,
okay. So yeah, so this state ideally what it should be, ideally what it should be, ideally it should be a target states, right? Then only it becomes de-entangled. So if all these four are our target states, then only we can write it in terms of this form, right? Hopefully this is clear. If this target states are same, then only we can write it in this format, right? This will be a target state in that case. If your target state is same. So what we're doing here, all the four states that we have reshaped, right? All the four states that we have reshaped, those are all same. The four target states, whatever you reshaped, are all same. So that is what we're trying to do here. So this operation, what we're doing, as in okay. So this target state expanded is our target states, and okay, this is the actual function, like what we're trying to do, the logic, what we're trying to do in the for loop. What we're trying to do is for j in the range 5000, we are appending a loss as 0, and then for I in a we have taken as a this state. For I in A, since we have four A's, so for I in A, we are appending the loss between the target state J and I of J, because that J is the sample and then I is the which indexing we are taking. Okay, and we are doing it for all indexing. All the four states are putting here, and it is having all the J indexes only, as in J as in particular sample index only, and then it's subtracted from the target J. Okay, so what essentially we are doing basically here is we are trying to minimize this loss such that the state psi is a separable state. It doesn't become an entangled state as in it is written in superposition. So what we're trying to essentially back propagate here, the loss function, what we're trying to get from here is basically this. This state will be a separated. This will be a separable state. Tensor protected with this. This will be our output state. This will be a separated state. Okay. So this is the logic of implementation. Hopefully this is clear. Is it clear?
yes, it is. It is.
Okay. Okay. Fine. And this is your training loop. So what is basically, so from here to give a certain kind of motivation, you will have four states, right? Four states that are similar to your target states, right? So you have produced four states that are similar to your target states. Means what? You have essentially done data augmentation. This is essentially a quantum data augmentation, as in you have produced a state that is similar to your target state four times. It is not exactly same, because we'll know that the target state is not exactly separable, but it is near to your target state. So if you'll apply an inverse unitary operation of this essentially can be used in your QGAMs as well, if you're getting the point, because the probability distribution of whatever states you have gotten will be lagbag similar, as in it will be in that Hilbert space only, if you are getting that concept. So if we'll apply a unitary inverse, whatever unitary or a combined unitary we have applied, if you'll apply unitary inverse of that, that will essentially produce a quantum encoded image or quantum encoding. When you'll reverse it to classical form, that will produce a new image in that subspace, if you're getting the point. So this can be having an application in QGAN as well, but this is the implementation. Okay, this is a vectorized form of that implementation to avoid. So if you put on this loop now, it will run forever. Like I have tried putting this, then I have directly inserted this. I want this as a logic. It came up with this code. So anyways, like you can try increasing the efficiency of this code, but this was the main logic that I wanted to incorporate. Anyways, so this is your training loop, and then the final is quantum predict. So you'll pass your test data here, and then like you will evaluate your test data. How many are the correct labels? Okay. So this is your training. And yeah, so this logic essentially, like there are various kind of logics of post-processing that you can do here. So as you already know, your output train vectors and your output test vectors from the quantum predict model, for the input vectors that you're passing and the input state vectors that you're passing will result in a 256 cross one vector. So there are like various, so you can do max voting here, you can do other kind of ML algorithms here, because you already have four states, right? Four states as in you have increased your particular data sets size here. So since you have increased that, so you can do other kind of algorithms, as you can do bagging here, boosting here, other, but since it's limited to four, you can try max voting itself. So max voting has been incorporated here. You can go through the code, like we don't have that much time, but so what this code basically does is, so whatever vector you have at the output, so what target vector you have gotten, that target vector is divided by 7. So to convert that into label kind of format, and this will give you a label. So this label is compared with your actual trains label, and then matching counts whatever they are, like it is summed and it is printed here. Similarly, it is done for the test data. You can try incorporating your own logics here, and the so so this okay. So this is your second approach. So what you just tried here now, after getting your target state, right, you can apply one more unitary. So this is the second approach that is followed. You can apply one more unitary, and then you can try to map it to actual target states, all the four states. So this essentially is an application of quantum data augmentation, because you're reshaping your input state to 50,000 cross 4, and then you're essentially increasing the data, and then you're applying a unit of segregation by SVD approach here. This is your SVD approach, which you can return a non-unitary M as label layer, and then like you're mapping your target states are essentially the target states required. So similar target states are taken here. This is unitary by SVD, and these are the states that we discussed on the first day. These are your states after mapping that you get. The quantum state vector final train and quantum state vector final states, but the accuracy that is gotten from this is also subpar only. So but I thought quantum data augmentation might yield in a better result, because since we are increasing the data size, if it is a neural network, or if you look into GAN architecture details as well, more the data size, more it will be the accuracy of the circuit. That is a general scaling law that it is following for now. So I thought it will be followed here as well for a linear regression, quantum linear regression case by multiplying with unitary. It doesn't follow that. But it is a research oriented field. Like you can try incorporating other as well, and the accuracy, you can try like researching what exactly are the accuracies. And these are the other methods that are tried. Many methods are tried. You can go line by line. You can ask that person, this line I haven't understood. I can explain to at that point itself. Okay, fine. And for verifications, we have again added a neural network layer here. Okay. And so if you look into, some accuracies are very low. This is your accuracy for some cases. We have tried incorporating normal like random measurement also. So as in the choice you have taken, right, out of the four, like you can take any choice of the target vectors, right? Out of the four you have, we have incorporated that also. That is the result. The 27% result that we have gotten, that is that result. So like we haven't gotten that much like good result from this implementation. So yeah. But if you will apply a neural network after that, the accuracy is 96.27%. So yeah, this implies that the degree of data set is still not changed, and we have just incorporated linearization in our data set. So we have failed to incorporate that non-linearity required for approximating or that boundary of segregation between our 10 labels. So this is the second architecture. So in this the case one is parametrical unitary of separation. Okay, so what exactly is different here? Just give me a sec. One case increase the number of parameters. Okay, okay. So with the activation function implemented, so like what we have done here basically is, now this is the conventional gate that we were following, right? If you look into, This was the conventional gate that we were following. Now, instead of this, what we can do is we can apply our own polynomial transformation here. As in, we can apply an activation function that represents a polynomial transformation on the QSVT. So I'll show it to you where it is incorporated. So it is incorporated in our this case as well, QiSVM case as well. Just give me a sec. Okay. Tuition function. Okay, ha. So this will come from the architecture. So yeah, yeah, I remember it just now. So this architecture we have incorporated basically. Not this. It comes at a later stage. After this, it comes in QI. I shared this file as with doc as with you guys as well. Yeah. So this is shared. This is also shared. So what essentially we are trying to do here is basically this is your parameterizable unitary. Now we know the basis. Like what basis we know is that this operation, basically this operation does some transformation on the unitary, the single values of the unitary, right? A polynomial transformation. So using that as an activation function between two unitaries. So this essentially, this total can be taken as one activation function. So what essentially we are doing previously, right? What previously we are doing, like we are taking this as one of the rotation gate, we're applying a unitary, then we are again applying this rotation gates here, then applying a unitary, and then so on. Instead of that, what we can do is we can take this rotation gates here at the start, then we are applying parameter unitary, then this will act as a parameter, like a polynomial activation functions. What it will do is basically it will apply a Taylor series expansion of the singular values of this A value matrix. And that essentially will be acting as an activation function for this unit. If you're getting the point, if you know about neural networks. In between two weight matrices, those are linear, there should be a non-linear activation function. So using that as the basis, this architecture I had come up with. And due to limitations in the speed, like we haven't. So okay. So this is the second architecture and first architecture. So okay. Okay, what is the difference here? I'll have to look into, but this is the architecture I'm talking about. So this is acting as an activation function. This complete unitary case, this completely unitary is acting as an activation function. Then you will be putting your unitary here, and then again repeating this continuously up till whatever like point you want. So that is essentially implemented here. The same operations are repeated in the for loop, and this indexing is done accordingly. So I have to go through the code, like go through over the code, but the same operations are there. There is nothing like extra. Only indexing you'll find to be a little bit like frightening, but it's not that frightening as well. If you put in the values, right? This indexing I had come up with after like 2 and 2. There are like many errors in the code. Yeah. So you can come up with a simpler indexing as well for this automation. Fine. Then the similar combined loss logic is implemented here as well. This is your current state, what you returned. That will be again the form 260, like it will have some 2 raised to 8 like elements. So, but your target is only 64, so you have to reshape that, and we already know what this reshape operation does in tensor product form. Okay, and this is your training loop, and this is your contemplative operation. And on this also, we have not gotten that much amount of accuracy. The architecture logic was similar. Like the polynomial activation function we tried to incorporate on the unitary. So this is an analog of a classical neural network. If you look into classical neural network, like I had shared the doc with you guys, I don't know, but classical neural network essentially is what it is the linear matrices. We are multiplying our input vector with linear matrices, then applying an activation function, then taking again a weight matrix, then again applying activation function of that. This all happens on the vector matrix vector multiplication format. So essentially, it applies an activation function after an operation done to the input vector by multiplying with the linear embedding or linear matrix. So here we don't have a bias. So here we have unitary. We are multiplying that with the input vectors, and then that architecture, what you will saw, the rotation gates and that unitary, then rotation gates, then that unitary, that essentially we are trying to take that as the activation function for our quantum case. That was the whole thought process for coming up with this architecture. This is an old architecture. It's not published anywhere yet, but the accuracy is also subpar. So you can try researching. And the remaining two models after this are basically, instead of taking that matrices as a parameterizable, you can take your matrices as the unitary of separation, what you've gotten from the input and output target vector space mapping, and then you can try parameterizing just the rotation gets in that case, the 4 rotation gets in that case. That has also been implemented. The architecture remains the same. The exact calculations are done in the forward method. So yeah, there is nothing. So these are all the methods what you implemented at the start, right? The indexing methods or the max voting algorithm and stuff. Those are all implemented here. You can go through. Like similarly, you like I don't know like what is the accuracy here. Let's see. Yeah, at least this accuracy will be equal to like one of the best. The best you can get with the unitary, it 87%. The remaining accuracy is what we saw in the past was subpar, and this is also good. 64 and 76%. So these are divided by 10,000. So these are also good accuracies. Okay. So at least this method is like you can explore this method. So first I'll share these two things. You can go into detail. I just tried to do the basic details and the implementation details like we have gone into in depth. This is case 2 non-parameterizable unitaries found by SVD. You can try finding by ML. You can try finding by QR. Same. Yeah. And again, you can check at the accuracy. What is the accuracy in this implementation? So fine. The same code is taken. Again, the efficiency is not taken into consideration once the code runs, like it's taken as the code that ran. So you can try increasing the efficiency of the code, try avoiding repetitions. That code is considered as a bad code. But yeah. Yeah, you can have a look at this as well. So this also gives a 65 or 62 and 65% accuracy, not that much yeah, accuracy. So but here, if you look into, this is your actual quantum algorithm implementation. As in here, your unitaries are not parameterizable. Here you're already finding that unitary, and then you're implementing, you're parameterizing just the rotation gates. So if you look into the code as well, uh, it's above. Okay, this is a separate. Yeah, so if you look into this orthonormal matrix were written, right? This is unitary by SVD. This is not taken in your initialization suburb. It's taken in the forward method definition. You have not taken. Okay, so this FCLS is just initialized here, but it's not used in the code anywhere. See below, like it's not used anywhere. So you have used your non-parameterizable unitary here, which is multiplied with unitary by SVD, which is the only changes in this code. Hopefully this is clear. Now, so this is a standard QSVT architecture implementation again. Yeah, the above cases that we discussed were like somewhat modification that we did. As in the first case, the modification was our unitary was parameterizable, all the unitaries were parameterizable. So in this case, it is not the case. Like unitary of separation is exactly found by SVD, and a polynomial function is also not used. Polynomial activation function is also not used, and only this is your forward. Okay. Okay. So you can go through the details. Like it might be a separate architecture that's written here that I came up with. Only minor changes are done in the code. You can go through this details. Like what exactly are the changes? The remaining combined loss also is remaining same. The remaining all implementations are same. you can come up with your own architecture layer. Okay, fine. If there are any doubts related to this, you can ask. And whatever tasks are there written in this, you can go through that. The main task that are coming to my mind is you can try changing the encoding format. Second is you can try changing the number of parameters there for I in the range 25, 26. You can try going to more depths. You can try coming up with architectures here. You can try implementing various augmentation strategies as in bagging, boosting that can be incorporated as a post processing for increasing the algorithm accuracy. And the main task for you is digesting what a QSVT algorithm is, because this is one of the crown jewel of quantum algorithms. Yeah, fine. That's all from my side. So if you can see like this is a random accuracy that we're getting for the implementation. Very bogus accuracy. So yeah, the implementation sometimes it works, sometimes it doesn't. But if you follow the logic and the architecture with the thought process, like how it was designed, so you'll get an accuracy that will be on par. So the 73% that we got, the accuracy that we got, that is one of the best accuracy by using QSVT. So yeah, and that is an OL algorithm. So, but it's still very much lesser, 20-30% lesser than the state of the art. Yeah. Okay, so your research task is to increase the accuracy, classification accuracy, come up with a novel QSVT algorithms. We'll try to share the two docs from our side. Anything else you want from our end?
No, no, no. If we'll first, I mean, like we'll first go through the code and understand it a little bit with comparing with the architecture, and then if any doubts were there, maybe I'll try to ask. Um,
Sure, sure.
that is what.
Shweta, any doubts from your end?
Uh, no, sir.
Okay, okay, okay. Thank you for the time,
Only
guys.
once. Okay, sorry.
Yeah, but please go ahead. Please go ahead.
Yeah, yesterday or today, any at any point of time when we are taking the data and actually making it unitary, we are leaving the values, eigenvalue components. If you
Yes,
observe, yesterday also I have asked the same.
yes, yes, yes.
So if there are two data samples wherein they have same matrices, uh, same singular value matrices on the left and right, and they
Okay.
only change with the eigenvalues. They only
Yeah,
change in
yeah.
the
That
eigenvalues.
that forms as a
What
adiabatic theorem problem. Yeah, yeah, yeah. Please go ahead.
what happens at that moment? So the prediction would be same. That is
Yeah, yeah,
typically
yes,
what should
yeah, yeah.
happen.
So yeah, yeah, yeah. So
But
like,
what if?
have you heard it? Like there are many unitaries that is possible. Like you can find any circuit depth unitaries that are possible. So if you're getting the point, means multiple unitaries can do similar mappings, same mappings.
Hmm,
So
hmm.
there are like I don't know the exact number, but there might be some research that will be done. But for a particular input-output mapping, there are many unitaries that we can incorporate, as in many unitary matrices are possible for that case. So if two eigenvector matrices are similar and you are saying the eigenvalues are differ for that case, then also that will form the unitary of that system.
Uh, okay, okay, okay. For the same data, maybe we would get a different
Yeah,
singular
yeah,
matrix.
but
You're telling that.
yeah, but if you look
Okay.
into this implementation, right, usually what happens is in Gore's algorithm, Shor's algorithm, there is a single state at the input, and then you will try to find a single state from that superposed state at the output, at least in Grover. And then from for the Shores, you will be having binary encoding of the two numbers, the decimals, and then you will try to produce that state at the output, the binary state of the output resembling the number, the decomposed number, if I'm able to recall the Shor's algorithm rightly. So this is one-to-one mapping. Of VQ also, if you look into, it is one-to-one mapping. What we're trying to do here is multiple to multiple mappings, as in multiple input vectors to multiple output vectors. So for this case, by using unitary by SVD, you will just get a single matrix. When there are multiple unitaries possible, when it is a single input and a single output mapping. That usually happens to be the case in quantum algorithms. In classification algorithms, we have a large data set. So for that large data set, we'll have multiple input vectors. So for this case per se, we'll not have that kind of situation, at least by using the similar method. By using different method, you'll get a different unitary and then the eigenvector matrices of that will be also be different.
Mhm.
Okay.
Mhm. Okay, okay, okay.
Okay, fine. That's all. But this is one of the crown jewels. So try to research. Like I have tried to give sufficient amount of motivation. So please. So what I can do. So please don't share it with anybody. But what I can try to do is share with you guys just this document. The document which saw at the start. So this is particularly for recommendation systems. It was a work done when I was with CDAC. It's a proprietary material, so I cannot share this document per se. But since it is with you guys and it's for applications, what we're doing is completely different from this one, and we're coming out with novel architecture in that. So this can act as a study material for it. And it has the references also. You can go through the references given in this as well. Okay. Yeah, yeah, yeah. You can go through the references given in this as well.
Yeah, okay, okay.
But don't share it with anybody. Let me check. Have I written the references? Yeah, yeah. So these names are also like this is the work done in US. Okay, okay. Thank you, Q&A, and references are there written. Okay, so these are the references. Okay. Okay. So I'll have to share the paper, my paper with you guys, but I cannot share my paper. My paper is a published paper, and that requires a certain amount of money. So I don't know, but it doesn't have. I'll try to do one thing. I'll try all the references are put in there. The same references you can follow. In that particular two references, two videos, YouTube videos, and one implementation in the paper is like in-depth thorough analysis of QiSVM algorithm, a grand unification theory. Even if you type now, grand unification theory in quantum algorithms, you'll get a lecture by I don't know the name, but the same author has the paper as well. So yeah, I'll try searching it now itself. Okay, but the time is above overhead. So if you guys have any like other questions, you can ask, or like we can conclude the meeting.
Yeah, nothing from my side. I'll study with you.
And okay, Britant has left the meeting. Britant, are you there?
Yes, yes, Akshay, I'm here.
Hi, Britant.
Yes, Akshay, I'm here. Hope I'm audible. I think there is a slight delay between uh, you and
Hi,
me.
Britant.
Yes, Akshay.
Okay, Britant, like with the last set of interns, we were unable to discuss with them. Yeah, so like with the last set of interns, the Q, yeah, yeah, you're audible, you're audible. So yeah, yeah, the connection works
Oh,
in
there is a
magic
lot of
ways.
below.
Brand new. So the last set of interns, now, Britan, I want to discuss one thing. The last set of interns, like we haven't discussed our formal, like how it will be. can be incorporated for LLM model. We'll try to have a session with them 15-20 minutes. That is like one of the main tasks. So yeah, at the end we can try to. Okay, a laptop is also hanging. So Sai and Shweta, bear with me. I'll just show you where that source is. Yeah, so Isaac Chung is his name, and he is an author for this. And you can find a paper of that author on like you can try searching in Google Scholar as well. So this is the video. There are like two more videos of 20, 30, or 40 minutes each. You can go through that as well in detail. Yeah,
Okay.
hopefully this is clear. You can find the similar author's paper online. Shweta and Sai, is it clear?
Yes, sir.
Please
Yes,
ask any
yes,
question if
it's
you have.
good.
Shweta, Sai, am I audible?
Yes, sir.
Okay, they left the meeting, I think.
Yes,
Okay,
yes.
is it audible? Yeah,
Yes, yes,
yeah.
it is
So,
audible.
yeah, yeah. Okay. Granular job paper is also there only. You can translate. Yeah, please do it. Okay, okay. Thanks for the time, Sai. Shweta.
Hmm. Okay. Hello, Britain.
Yes, yes, I. Okay, so
Uh,
I think we should. Sorry, I think we should close now. It's too late. I will inform Akshay. Okay, bye.
I've got the paper. Actually, I asked regarding. Yeah, I wanted to
Okay, you
ask
got the
regarding the
paper.
paper. A grand unification of quantum algorithms by Isaac L. Chuan. I got the paper. Is it 38 pages or 39 pages? Is it the one which you were talking about?
Might be. I'm not sure, but please ask in
Okay.
the group that he made with you, right?
Yeah.
So put it,
Yeah. Okay.
put that paper into that group, and I
Yeah.
think
It
we
actually
should
looks like
close.
that.
Hmm.
Okay. Yeah. We,
Okay, so good night.
good night. Thank you so much. It was actually so nice. I thought of telling it to. Yeah. Yeah.
Okay, okay, I will inform him.
Please do convey that. Yeah.
Yes, yes. Thanks. Bye.
Thank you. Bye.